Let's talk about chapter 2 is all free vibration of single degree of freedom systems. So we are looking at free vibration of 1 degree of freedom system. All right, so vibrations, again, these are just an exchange of energy between potential and kinetic, and requires oscillatory motion. And it can repeat itself, what we would consider like regularly or irregularly. So that's what we call stationarities in vibrations. So if the motion has a signal frequency and amplitude, it's called simple harmonic and represents a basic form of vibration. So simple harmonic has a single frequency and amplitude. Right. So you can have for a 1 degree of freedom, simple harmonic motion is defined as a periodic motion where the restoring force is proportionally equal to the direction and opposite that of the displacement. Right. So let's go ahead and look at what a periodic motion is. Just something that's going to repeat, and a simple harmonic motion is just going to be your basic sinusoid. Right. So I like to do it like this. If you have a system on a fixity and you have a spring and you have a mass, right? You can go ahead and put this on a timeline. T, and you can have a periodic motion, right, which may look like this. Let's go like that. Right, so this is periodic. And it's periodic because it repeats itself, but it is not simple by any means, right? Does that make sense? And you see how this mass is kind of moving up and down, and then this is how we build the plots out behind it.
Professor, is that a true example where a one mass, one spring system can have like compound frequencies?
Yeah, if you're forcing it, and if you've got a forcing on it, definitely. So let's go ahead and look at that then for a simple harmonic motion. A simple harmonic motion, right? Whoop, would look like that. That makes sense? So you got one frequency, and you have one amplitude. Let's just call it simple harmonic.
Is it possible to design a spring that looks the same as its harmonic graph?
I'm not sure. Say that again.
Okay, so you know like how weird the first graph looks?
Yeah.
Is it possible to design a spring that represents physically how its graph will look? Like if I made a spring that...
What if I do the political answer here and say, in this class, we only use ideal springs, right? You can do anything. I believe in you. Like dirt bikes have like multiple spring rates, but that's a whole different ball game. Does that work for now? It's good enough. Okay, so given all right, so let's talk about a little bit about mathematical space, right? So the space we operate in is kind of like x, y, z with time. Does that make sense? When I talk about mathematical space, we usually plot something with x and y. What's x commonly? Time, right? And then y might be like temperature or blood pressure, or something, right? So we want to, in the plot we're going to draw here, we're going to use the space omega nt. Okay, so our x-axis is going to be omega nt, so it is time, but it's multiplied by the natural frequency of the system. Does that make sense? Okay, so given the simple harmonic motion concept, right, of constant amplitude and constant frequency, the wave starting at point O, right, so let's call this point O, can be modeled as the point on the end of a vector. So let's go ahead and model a vector. And let's go ahead and model this point, right? So can be modeled as the point at the end of a vector from the origin of a vector with length a. So our vector has a length a, rotating at a constant angular velocity, omega n. Whoa. I don't know what just happened, but something happened. Oh, I zoomed in. Okay, rotating at a constant angular velocity, omega n, right? So we have a point on this vector. Our vector is rotating at this initial angular velocity, omega n, where the angle from the origin of the vector, this angle is phi. Oh, that's not how I draw phi. I'm sorry, how do I? Where the angle of the origin of the vector is phi, and that's going to equal omega t, right? So our omega is our lowercase Greek letter, and phi here is our lowercase Coptic letter. You can also draw it like the Greek one, which is like that. I just don't do it because it just looks like a scribble, right? That by the end of the semester, that won't look like anything. So I draw it with a circle with the line. It's not theta. So theta we will use later. So if you want to call it theta now, that'll mess you up. So I just promise you, please don't call it theta. It's phi. So what this gives us then is if we rotate this point around our circle, right? Not the best circle, but if we rotate this point around the circle, what we can start to do is build a sinusoid in our space, which is omega nt, right? And we'll have a sinusoid that looks like this, right? So amplitude, what is amplitude? Is amplitude measured from here to here? No. Why? Because it's the length of the vector, right? So as the length of the vector, it's going to be measured from here to here. That makes sense? So your amplitude, I'm going to draw it on the bottom, just because I've got more space, is going to be looking like that, right? So you're going to get through pi into 2 pi. So let's go ahead and just put 2 pi on here. And then let's go ahead and put 4 pi on here. Okay, does that make sense? So as we're oscillating through, you have 2 pi and 4 pi. And then whatever point you're at, right, you can start to see that you can get the amplitude or the distance x of whatever your point you're at is a sine omega nt. Right, and this is just kind of a visualization in this omega nt space. And the core concept here, okay, but the core idea here is that we're just rotating around a circle, and that's how we get our simple harmonic motion, right? So it's always going to be sinusoidal because we're always rotating around a circle. Go ahead.
What's the relationship between natural frequency and omega? Because p is equal to omega t, but there's this omega n going around. Are they the same thing?
No. So it's better in the next one.
All right.
Right? So this is just going to be based off your angle, right, for these simple harmonic motions. So again, what we want to see here, the main point is that it's harmonic. Does that more or less make sense? Confusion level relatively high. Okay, this is always a confusing concept, but just get the idea that it's harmonic and we're moving around a circle. Okay, so remember from the first day of class, what's the best way to solve an ODE? To guess, right? So we're going to solve our ODE. We're going to solve our ODE here by guessing. So the mathematical modeling of free vibration. Okay. So the development of a mathematical model for a system under free vibration, right, would allow us to predict and model the vibrating system of interest, right? So that's really what we want to get to. So let's go ahead and just assume I forgot my bearings. Assume our system, right? X positive to the right, mass frictionless, spring constant K. Right? So what's this equation of motion? Yeah. So equation of motion is, mx double dot plus kx equals 0. Right? And so this is an ODE, correct? This is a homogeneous ODE. So we want to solve this ODE. So let's make a guess. And the best kind of guess is an educated guess. So let's go ahead and look at how a system vibrates and see if we can build an expression or a series of expressions that will get us to a formulation that is not an ODE and that is something we can test, right? So that's what we want. We want to make a series of assumptions to get us to a formulation that is not an ODE and is something we can test. So go ahead and draw out your space here, T and X. All right. So see if you can draw something that looks pretty much like this. We're going to cross our line up here at the top, and we want to be coming down into it. And then we want to come down and up, and whew, that is brutal.
It helps if you exhale while you draw it.
If you what?
Exhale while you draw it.
I'll try that because I need something. Okay, so this is an oscillating system. Let's go ahead and define a few things, right? This is going to be x0, correct? Everyone see that? It's going to be our initial displacement. What's our initial velocity? Wait, I'm calling. Igor, are you here, Igor? Yeah, what's our initial velocity? No. So omega n's our natural frequency. How do you get velocity from displacement?
Right. You derive it.
The derivative?
Yeah.
Yeah. So we want the slope of this line, right? So our velocity is going to be v naught, right? Now our phase, because last time our phase was in the omega n space, right? Our phase, where this starts in relation to this, is going to be phi over omega n. Does that make sense? And that's how far back we're starting. Okay, so here to here, this is called a what? What's this distance? 2 pi. Not anymore because we're in time.
Oh, period.
Yeah, period, right? And we denote that with a T, capital T, right? That's what you guys use. And then at any spot again, we're going to have a sine of omega nt plus phi. Right? Okay, where is our maximum displacement? At the peak. Pretty easy. Then where's our maximum velocity? Anywhere it crosses, right? Say that again?
Anytime the slope's vertical, right?
Yeah. So so our slope is the most vertical here. So as I come up, my slope flattens and gets more vertical. Would be better if my line wasn't so crappy. If I lost instead, I exhaled, I keep trying to remember that, and then I keep drawing, and I don't. Because that's how it works. Okay. So this system does a few things, right? So the system oscillates. How would you model that? Someone else. Yeah. What's your name? Well, you got to answer the question too. What?
Max displacement.
Oh, this? Yeah, sorry, that's max displacement maximum displacement. But what's your name? Nick. This is going to take me a while. I really apologize. But okay, Nick. System oscillates. How would you model that mathematically? If you got something that's kind of this shape and oscillates, and you're told to draw that, what kind of function is that? Yeah, like a sine wave, right? Just model it as a sine. It's like a sine function is a great answer for that. Right? So the system oscillates at a different speed. It's one speed throughout, but we can change the speed, right? So system oscillates at different speeds. Okay, who's in the back? Very back. We're just going to go around. Yeah. Alberto. So the system oscillates at different speeds. How would you model that mathematically? You kind of need to make an altercation to the sine function, right? And so if you put a time inside the sine function, maybe we could multiply the time function by something. Slow down our time, right? Because when your time is 3.14, you're way past time. So we use a parameter to adjust omega n. So okay. I thought okay. That would have been a great segue. Okay. Anyways, so use a parameter omega n to scale time, right? All right, so our system has different amplitudes, right? So how do we adjust for that?
Multiply the sign.
Yeah, multiply the sine by a constant. Multiply a sine by a constant a, and then, okay, gentleman in the red shirt, what's your name? Will.
Yeah.
That's Nick and Will. And what's your name?
Brandon.
No, I got
Try.
Trey. You look the same to me. Okay. Will. So we have different phases. How do we adjust for? We have a system that's starting in a different phase, right? So how can we adjust for the different phases? What do we need to offset here?
Offset time.
I'm asking Will. Okay.
The top. B.
What?
B.
Say that again.
B.
V.
B.
Phi. Yeah. So, but what do we want to offset though? Like what's the purpose of phi here in this equation?
On the other side.
Yeah. So we have this offset. So we want to move the time function up and down in our sine function. We want to move the time variable up and down in sine. So sine is a constant. It's going to give you the sinusoid. We scale time with our omega t, and we offset it with our phi. Right? So the system has an offset. So use phi for offset. Okay, that gets us to 230. But we end up with an equation, I guess. Let's write the equation. So x of t is equal to a sine of omega n t plus phi.